Ask questions as you see it. This is number 8. So we're looking at this is using, and it's got these crazy units, but it's what I like about it is it's using this this impulse and momentum and all this stuff is combined along with some crazy units. So it says how many pounds of force, if you don't have your paper at home, how many pounds of force must a batter swing her bat if she wants to hit an 85-mile-per-hour fastball or a fast-pitch softball. It gives us mass in slugs. And remember, the mass of anything in English units is slugs. The mass, it's an old medieval term. The mass in English in metric units is kilograms. We're more used to that, but slugs means the same thing. If you look at your magic triangles on your equation sheets, it has a thing with slugs as the mass, 32.2 feet per second squared as the g, and then pounds as the force. So that's the F equals ma for English units. So it says how many pounds? Okay, she's going to swing directly back at the pitcher 150 miles an hour. So a little drawing here will help. And the reason why you want a drawing is to get your signs and your directions down. So this softball is coming in at 85 miles an hour. And then hit, and here's the key, it's hit back. So there's a direction change. It's hit back at 150 miles an hour. So to label these, that'd be my V naught, and this is my V final. And so the mass of this ball is 0.025 slugs. I mean, my mass is around 6 slugs. Because you take your my 6 slugs and multiply by 32.2, and now you're up to about my weight, 190 or so. That's all we know. And we're trying to figure out, if this is the baseball bat here, how many pounds of force we're having to give this ball to get it to change its, not only its speed, but its direction. Oh, one other key factor. We know it's in contact with the bat for 10 milliseconds, which is really a long time for a ball to be in contact with the bat. Okay, so the question is pounds and force needed to do this. So we go back to Newton's second law, original second law, maybe start there. And also impulse, since time's involved here. We can let's go with Newton's original second law. It says force equals the change in momentum over time. And since I have time given here, I'm going to have a change in momentum. Boy, that would do it, wouldn't it? It looks like it's conceptually not that bad. So this is the same thing as saying mass times change in velocity over time, and that'll give me my force. So let's go for it here. We have unit issues. I'll show the shortest way to attack this. So force then, this really is not necessarily impulse at all. We're not asking for the impulse. Just using Newton's original second law. So let's go ahead and plug it in. 0.025 slugs. And then my change in velocity. Now here's where you got to be careful. And students have come in asking about this one, and invariably it's because they took 150 minus 85. You can't do that, because I can show it as a positive 85 here because I have the directional arrow. But in an equation, I'm going to have to show that if that's my V naught and that's my V final, I'm going to have to show that as a negative 85 to show its direction. So it's actually 150. I know my units got issues here. 150 miles per hour minus a minus 85. So adding that, and then divide that by 10 milliseconds. I'll go ahead and put that in seconds. 0.1 seconds. And right now, if I just plug these numbers in, I get the wrong answer because the force is in pounds, but pounds means you're not dealing with miles per hour, you're dealing with feet per second. And so instead of go ahead and convert this into feet per second and this into feet per second, why not just convert the difference into feet per second? And so this is the same thing as saying, I'll go and do my unit analysis right there in the problem. 0.025 pound slugs times, now the difference is 235. And I want to go ahead and just right there in my problem, do my little unit analysis. And I went up in feet per second, so I'm going to say 5,280 feet per second times my, might as well do this now, well, it's going to get feet into miles, I guess. 5,280 feet in a mile on top. Yeah, need more room. Okay, and then now let's go ahead and get this in there. The difference is 235, and that's positive because minus and minus, 235 miles per hour. And then convert my hours into seconds. And so, whoops, seconds go, uh-oh. I want it feet per second, so I should be okay. So where's my mistake here? Oh, hello.
Feet shouldn't,
You got,
yeah, feet shouldn't cancel.
what am I doing here? All right, so I'm totally screwed up. And I'll edit that out, or I won't. I don't know. So there's at least I was careful and looked and saw. Of course, you guys didn't say anything, daggone it. What's he talking about? 5,280 feet per mile. Should have done that right there off the bat. And then now I can go ahead and put my miles per hour in. So it's 235 miles per hour. And then you got hour over 3,600 seconds. Double slash, I'm done. In that parentheses, divide by 0.01. And now I should be ready to say my answer. We can punch all it in. Do a little Martha Stewart and go right to the answer. We are at 862 pounds. I hope I'm right. So all that works out to a force of 862 pounds. That's a lot of force put on that softball. 862. So there is number 8. Looking at it turned out it wasn't even an impulse problem. It turned out to be a Newton's original second law problem. Any questions from the studio audience? Okay. That's the end of that video.